Ја имам ретката чест да поканам гостинка која што далеку пристигна да предава за една тема што верувам дека сите најмногу ве интересира. Доктор Салис Најмен ќе ви држи предавање за матичните клетки и нивниот потенцијал за третман.
Good afternoon, everyone. Are you still awake? My name is Sally Snyman. I'm originally from the UK, a medical doctor, and I've been working as the medical officer for Esbright Group for the last few years. I took a slightly unusual route into cord blood and stem cell banking via anesthetics. It's a long story. So I am not a stem cell specialist, but what I would very much like to do is just to introduce you a little bit to what is out there and what is happening, because there is a lot. So I'm going to approach the subject very much from the point of view of a private stem cell bank. But I want to mention the hope, what is the potential for stem cell therapies? And I'm going to focus primarily on the areas of interest that we have today, which is rare diseases and pediatric disability in general. I think, as everybody knows, the vast majority of stem cell therapies over the last 40 years now have been focused on hematological disease, primarily cancers, allogeneic transplants from bone marrow stem cells. But now we're going to look at what's happening in the regenerative medicine side, which is quite different. I'm going to mention a little bit about some new technologies which are coming online, which many of you will be very familiar with, and I would guess some of you probably not so much. And what is happening there on the research front, but most importantly, what is the reality today? What can you do today with stem cells? What is in the pipeline? And what can we do, and what can you do to make sure that you know what's going on and that you are ready when these therapies are available to apply them to the right patients at the right time? Then I'm just going to mention a little bit of my personal experience, or our personal experience within CryoSave. We have actually managed to release some samples. We have treated patients with them, which is very exciting. And finally, just give you a few resources so you can keep track yourselves of what's going on. So as I said before, I'm going to limit this talk to this scope. So rare diseases, and for the sake of simplicity, I'm calling rare diseases largely genetic, having a genetic basis, a pediatric population, and these diseases are usually disabling and chronic or progressive. And then there's another group, the acquired disabilities, and under that group I would include cerebral palsy, the hypoxic ischemic encephalopathy, which is probably linked, acquired auditory loss, and interestingly, autism and potentially trauma as well. Now, these have all been under the scope of stem cell therapies to a certain extent, but with these new technologies, we're moving on from simple cell therapy to look at tissue engineering, regenerative medicine, reprogramming of cells, and ultimately gene therapy as well. So just a quick recap. What is a stem cell? What are we talking about? Well, these are the building blocks of all tissues and all organs in the body, and it's nature's way of healing tissues and repairing tissues, not only from the point of growing an embryo, from the point of conception, but all through our lives. We all have stem cells in our bodies, everywhere. Surprisingly, our fat tissues is a very rich source of stem cells, which I think was a surprise to many people and came to light not so long ago. There are, of course, different types. The most important differentiation is between embryonic or totipotent stem cells. These are the ones that you find after fertilization of the ovum in the first few days of development of the blastocyst in the embryo. These cells can renew themselves, and they have the potential to form any of the something like 216 different cell lines which are present in the adult human body. And then the other sort, which is what we're most interested in, is the somatic, or so-called adult stem cells. Now these, after a while, stem cells become less totipotent. They're still pluripotent, but they're more limited in the range of cells that they can develop into. And this starts to develop largely along the three germ layers of the embryo, so the ectoderm, the mesoderm, and the endoderm. Now these different layers of the embryo develop different groups of tissues, if you like, And over time, stem cells will limit themselves to smaller and smaller groups of cells into which they can differentiate. But all the time, they maintain these basic qualities, i.e., a stem cell can always renew itself, produce another stem cell, and it can also differentiate into different cell types to form tissues. So where do we get them from? Well, as I said before, most stem cell therapies are for hematological disease. So these are using hematopoietic stem cells, the ones that form the blood components, the red blood cells, the white blood cells, the immune system, platelets, and they are found primarily in bone marrow, also in peripheral blood, particularly when the bone marrow has been stimulated with GCSF, colony stimulating factor, to produce stem cells faster, and also from cord blood, this waste product at the time of delivery of a baby. Other sources, we also have mesenchymal stem cells, which are becoming increasingly important now in regenerative medicine, and they can be found in fat tissue, so fat is not a complete waste. They're also found in Wharton's jelly, which is that jelly substance you find in the umbilical cord itself when the baby is born. And of course, you do find some in cord blood as well, although the hematopoietic stem cells certainly dominate in the cord blood. Now, these mesenchymal stem cells have the potential to develop the connective tissues. So here we're talking about bone, cartilage, fat, and they also have properties of being immunomodulatory, which is becoming very important in regenerative medicine. And then, of course, there are other cells which we don't fully understand yet, which you find in all sources of stem cells, particularly in cord blood, cord tissue, and bone marrow. And these are the endothelial progenitors, which have the potential to grow into blood vessels. We also have precursors for neural tissue and various others. So, first of all, I'd like to focus on the acquired disability group. Now, this is a group of patients where there is no fundamental genetic abnormality. This is disability due to an external insult, be it hypoxic trauma during birth or some other external factor normally. Now, they have been treated with stem cells for some time, and normally what's been happening is that they've been treated with straightforward infusions of hematopoietic stem cells and others from bone marrow or from cord blood. Now, what is the mechanism here? I mean, this is the beginning of regenerative medicine. The idea here is to stop the pathological process, potentially reverse it, and even regenerate some of the damaged tissue. Now, the mechanisms of action are not entirely clear, but it seems to be a combination of depressing inflammatory processes and then potentially regeneration of damaged tissue as well. This is largely mediated by mesenchymal stem cells, and these therapies are always autologous because you are basically using your own stem cells to regenerate tissues that have been damaged. This is the safe way to go forward, of course, because with autologous stem cells, we have no inherent genetic defect we need to worry about, and by using your own cells, you avoid graft versus host disease and immune issues, which of course is the real problem, the bête noire of any transplant medicine. However, autologous therapies are a form of personalized medicine. Now, in my line of work, of course, I'm talking about private cord blood banking. Now, this is for a lucky few people have their stem cells stored in a cord blood bank. I think the oldest person with stem cells stored is around 20, so that leaves quite a few of us baby boomers and Generation Xers who will never have such a luxury. And as I'll show you later on, there are other ways of harvesting autologous stem cells, but this is a very labor-intensive and personalized process to develop a product for one patient. So the real goal here is to move away from autologous therapies and to develop allogeneic therapies, off-the-shelf products, by overcoming the immune problems and offering potential therapies to everybody, which will be far more practical and far more cost-effective. So looking at cord blood now, and I talk about cord blood because this is what I know, it is used in over 70 standard therapies. It has been used in 70 different diseases. The vast majority of these are still hematopoietic, and the vast majority of these uses have been allogeneic cord blood from the public cord blood banks, which you find all over the world now. Therefore, they have mostly been for allogeneic transplant. But I put metabolic disorders in bold because it is already being used for metabolic disorders, and this is one of the groups of rare diseases that we are focusing on today. Excuse me. And these therapies are already used in adults and children. Now, if you're interested in following this, there's a very good website, an American website, set up by a woman who used to work for NASA, whose young daughter died of leukemia, and she set up the Parents' Guide to Cord Blood. It's a non-profit organization. It covers cord blood uses from all sources, the public, the private, the allogeneic, autologous, and she keeps a very good up-to-date database of different cord blood banks, different clinical trials, different indications for use, and this is a very good, neutral, independent resource if any of you are interested in following this. So just to touch on some of the new technologies, as I said, I am not an expert, and it is a very complex, fast-moving field, but just to give you a summary, a little taste of the things that are happening, we are now moving, for stem cells, we're moving towards regenerative medicine, and that's really to replace worn-out and damaged tissue where there is no genetic defect, and this is what we've just been talking about, the autologous therapies for cerebral palsy and ischemic encephalopathy. But we're going a step further now. There are options to actually engineer tissue. We're talking about three-dimensional structures here. There are scaffolds being developed that are being seeded with stem cells, and then you actually grow the tissue in ex vivo, in vitro, and then you actually develop a piece of cartilage or an ear or whatever, and then you would transplant that tissue back into the patient, which would have no immune problems and would behave from that point on like tissue accepted by the body. And then, of course, in 2012, there was a Nobel Prize for the IPS, the team Yamanaka and his colleagues, who actually demonstrated production of IPS cells. Now, this is induced pluripotent stem cells. So what they managed to do was to take mature adult cells, in this case actually fibroblasts from human skin, from adults, and they reversed the process completely, and from those mature cells produced embryonic, totipotent stem cells, which was pretty amazing. This is something no one had ever done before. So this opened up a whole new possibility. If we can do this with adult cells, what does this really mean? We can now reprogram cells into any tissue that we want, in theory. So it's very exciting, but let me put a big proviso on that. There are a lot of barriers, a lot of problems, a lot of questions to overcome before this really becomes real-day therapies. And then finally, also, I think one of the most exciting developments of all is gene editing. The CRISPR technique now allows us to go into DNA and to sort of cut and snip and take out pieces of DNA and to edit with healthy DNA to actually repair faulty genes. That hasn't come through properly. That's supposed to have bars on it. Never mind. Oh, here we go. This is just to show you how the number of clinical trials using perinatal stem cells, and here cord tissue and cord blood, have actually increased over time. And this is for non-hematopoietic diseases. So this is regenerative medicine. So these bars are from around 2011. And then 3 years later, the number of trials has virtually doubled in all areas. So we're talking about autologous, allogeneic, related, and unrelated. And now next year will be 3 years on again, and those numbers, I promise you, will have increased again. So there is a lot of activity, and we're getting closer to the clinic. So just to have a quick look at tissue engineering, the idea here is to harvest stem cells, usually mesenchymal stem cells, from fat tissue or from cord tissue, to expand them and grow them, and they grow very, very well in the lab on plastic. They're very robust. And then to seed them onto the scaffold and then use various growth factors to guide that tissue differentiation into bone or cartilage or whatever it is that you're after. Now this is just a photograph from my colleague. We have a PhD scientist at CrySafe who helps us with not with research, but with finding out what's going on and improving our processes and generally supporting and looking ahead all the time. And this is something he did a few years ago. He actually produced neural tissue on a scaffold, and you can see on the left there the action potentials from active neural cells. So we can use tissue engineering for autologous implants, and they're also beginning to use it for allogeneic as well. And this is very important for wound healing, a massive, massive worldwide problem, chronic wounds. And this is an example. This lady was, in 2008, she received the first tissue engineered tracheal transplant. She was a 30-year-old woman. She had a bronchomalacia, and they used a decellularized cadaveric trachea, which they cultured with her own mesenchymal stem cells, and they transplanted it back into her. And there was an article in The Lancet 5 years afterwards, and she's doing really very well indeed. So this is real. This is happening now. So here, just to mention IPS again. So again, just to show in diagrammatic form, what they're doing is they're taking adult cells and they're reversing the differentiation process right back to the beginning. So you've got an embryoid body, a totipotent cell, and then reprogramming those cells to form different tissues. So just to dampen the enthusiasm a little bit, because it was incredibly exciting the last few years in the stem cell environment. There has been a dark side. There were publications that were retracted. Nothing is ever quite straightforward in this game. And then later on, so two papers were retracted. This is a technology related to IPS, not exactly the same. And then we move forward again. And now here we find, back in Japan again, in the same clinic, they actually started clinical trials using autologous induced pluripotent stem cells for the treatment of age-related macular degeneration. So this is a big problem, visual problem in older adults. So here we can go on about IPS a bit more. Now it gets complicated, of course. Now you can differentiate, you can choose your cell line, and then if you want to, you can start to potentially edit the genes as well. So now you potentially, having started with a simple stem cell from cord blood or bone marrow and infusing it into their blood to become bone marrow cells, you've now potentially using something like a skin cell or something else to produce a completely new tissue, which you're then editing genetically. So it becomes super complicated, very complicated. And this is where, so I've already mentioned, hang on, okay, just wait a minute. So this is where the regulatory side comes in. So one of the big hurdles that we have to get over is to ensure that these therapies are totally safe, but without putting so many hurdles in the way that they're never actually going to reach the clinic, and we don't get the efficacy of these exciting new treatments. Gene therapy, introduction of editing the DNA. Now there are several options for gene editing. You can either do it right at the beginning, pre-implantation to the germ line, which is kind of selecting embryos based on healthy cell lines. Or it can also be applied to somatic cell line manipulation. So you can actually produce cell lines which can treat patients who already have some genetic defect. This is not affecting the entire body. It will usually affect one tissue and it may or may not be permanent. But the big problem with gene editing at the moment is how to get these new healthy genes into the cells where they're needed. We need a vector. And they've tried different types of viruses, and there have been problems along the way. Some of the adenoviruses have been very good, but there's a big risk of immune reactions here, and there was, I know there's at least one death in the past from very major immune reactions. They've tried the smaller lentiviruses, which are very good, but they're very small, and therefore you're very limited to the amount of DNA you can actually carry in these vectors. And messenger RNA is the future hope. Sorry. Okay. I'm sorry. So just to put all these variables on one table, what I've done here is I've compared the different therapies on the left with a stage of development across the top. So the first step for all of these is the scientific discovery and the publications. And then we get to a stage where we move into animal models and animal studies. From that point, they move into man, first in man, clinical trials. And then eventually they develop new therapies. So looking at the different therapies on the left here, at the bottom we start with the simple cell therapies. So this is what we're doing now, infusing straightforward cord blood or bone marrow. Then we move up through regenerative medicine to reprogramming, gene therapy, and the more complex mechanisms. So if you just look at this with your eyes half closed and look at the density of the crosses, the more crosses, the closer we are to the clinic. So you can see at the bottom that we have real therapies, transfusion of bone marrow and cord blood, and towards the top we are a long way from the clinic. And the real difference is the actually increasing regulatory burden as you move up. So this is where we need to look. This is going to probably be the rate limiting step as to how quickly we can get therapies into the clinic. Now, here in Macedonia, you have your own regulatory environment, and we are in Belgium, we are in the EU. Switzerland, we're not. And a lot of these samples we have released to the US. So as an international bank, we have to respect the regulatory environment all over the world. Now, as usual, America is leading the way, but the EU, Europe, is also pretty advanced in regulations. This is a list of directives that were published back in 2004 and 2006 to actually determine how to handle human tissues for the first time. How are they procured? How are they tested? How are they stored? How are they traced? And then recently, they've actually looked back at labeling and coding, and also establishing equivalent standards of quality as they look more towards an international market. So the idea here is that you will have treatment centers in one corner of the world, but if we're handling our tissues and cells the same way, we will relatively easily be able to transport them to other countries, and they will still be able to be used for therapy. And then looking back at our levels of complexity, we have the simple cells, and then we have the ATMPs. Now, this is a group of therapies called advanced therapeutic medicinal products. These are the ones which I was talking about, which have been manipulated and which have undergone all sorts of different procedures, which introduce a level of complexity and a level of potential danger at each stage. In 2007, the European Union introduced legislation specifically regulating ATMPs and the requirements for good manufacturing practice based on the pharmaceutical model adapted for human cells and tissues. In the US, they do it